Hello, I'm Madison. Today we are going to talk about the physics of diagnostic imaging. Diagnostic imaging, or medical imaging, uses electromagnetic radiation and other technologies in order to produce images of the inside of the body to assist healthcare staff in diagnosing illnesses, abnormalities, fractures, etc. Medical imaging branches off into a few different types, such as MRI scans, MRA scans, CT scans, ultrasounds, X-rays, mammography, arithrogram, myelogram. I will be going over only a few of these. In Wilhelm Conrad Röntgen and the Early History of Röntgen Rays, O. Glacier quotes a message from R. Neuhaus on his reaction to the first X-ray images from Röntgen. Neuhaus says, "A compass in a metal box had produced on a plate a black picture of a magnetic needle. Another picture showed various steps of a shadow scale which had been formed by a ladder of tinfoil. A set of weights enclosed in a wooden box and covered wire spiral wrapped on a heavy wooden block showed distinct pictures of the metal but only weak shadows of the wood. But the most curious picture is that of a human hand." Glacier, 1993, page 30. This was only the beginning of medical diagnostic imaging. 1890s. Wilhelm Conrad Röntgen, a physics professor at the Physical Institute of University in Würzburg, discovered X-ray on November 1895. The first clinical intent X-ray was said to be recorded not until January 1896 by two Birmingham doctors to show a needle that was embedded in a woman's hand. In the General and Queen's Hospital, casualty surgeon J. H. Clayton operated on the woman's hand to remove the needle, this being the first X-ray guided operation. 1930s. Experimentation with radiopharmaceuticals began. This was an injection into the body of gamma-ray photons which were detected by radiation. 1940s. In 1946, nuclear medicine was introduced to the public, where radioactive isotopes, or radiopharmaceuticals, were then distributed for medical purposes. In 1947, the 2D ultrasound was discovered, and the first ultrasound was done to see a myoblastoma in a leg. In 1948, the first nuclear medicine scan was done on a thyroid gland. 1950s. In 1950, Canson et al. Discovered the scintillation detector, which detected inorganic calcium tungstate. In 1951, the gamma-ray scanner was introduced. In 1957, the first electronic gamma camera was introduced by Anger. The first mammogram was said to have been discovered by Solomon in 1913, but the idea was abandoned until the 1950s. 1960s. In the 1960s, clinics began to use position emission tomography (PET), but was discovered years before. In 1963, Comrack was said to have been performing experiments with computed tomography (CT) with laboratory experiments, where he later accepted a Nobel Prize of Medicine with Hounsfield in 1979. The first actual concept of computed tomography was originated by Randon in 1917. 1967, Inger discovered the single photon emission computed tomography (SPECT) could be used with the gamma camera. Anger announced the discovery that the electronic gamma camera could be used for rectilinear scanning to conduct multiple plane longitudinal tomography in 1968. Mammography was picked up again to diagnose early development of breast cancer. 1970s. At the British Institute of Radiology annual conference in 1972, computed tomography, or CT, was introduced. However, the inventor of the moving discovery still is pondered upon. This is said to be the most significant move forward for radiology since the discovery of X-ray by Röntgen in 1895. 1980s. In vitro cross-sectional images were discovered in the early 1980s. Historic information derived from Webb, 2012, page 3 through 8. X-rays are a part of the electromagnetic spectrum as they are a form of electromagnetic radiation. They have a high frequency rate and high energy levels, allowing them to easily pass through objects. In order for electromagnetic radiation to occur, the electric charge must be continually moving. When an X-ray is developed, it is because the electrons in the atom are continually moving and the level of energy within the X-ray is dependent on the distance the electron traveled between orbitals, this distance being delta X, the location of uncertainty in Heisenberg's uncertainty principle. As the X-ray photons come into contact with the atom will absorb the energy of the photon into an electron, where the electron then is moved into an outer orbit around the atom. The energy levels have to balance out within the atom or the photon cannot remain absorbed. When it cannot balance out, the photon will be rejected and the electrons will continue to orbit around the atom. When a patient is being X-rayed, they are positioned between an X-ray source and an X-ray detector. X-rays are sent through the body in a localized area, the photons pass through the atoms in the body, and depending on the structure, bone, tissue, air, fat, etc., the photons will be absorbed at different levels. An image will then be produced on an X-ray detector showing where the photons were most absorbed in bone, creating obvious shapes along with varying shadows where the photons were less absorbed. The bones on an X-ray show up the most defined as they are made up of calcium, which unlike other parts of the body, they have a higher atomic number allowing more photons to be absorbed. Here we have an X-ray tube, which is used for a few different kinds of diagnostic imaging. At the top is a high voltage supply. It is connected to the cathode and the anode, and its purpose is to accelerate the electrons that are emitted from the cathode towards the anode. The cathode filament in the orange is where thermonic emission occurs. This meaning the filament being negatively charged will produce and emit electrons. The anode or the target in blue includes the anode, rotor, and stator, and as it moves it creates heat. As the electrons reach the surface of the anode, they are converted into X-ray photons. The purpose of the lead shielding is to contain the system as the electrons and X-ray photons are scattered, directing the photons to the filter. The lead shielding also absorbs radiation. As the electrons are converted into X-ray photons, they end up with a varied level of energy. As they reach the filter, the photons with lower energy are filtered out, allowing the higher energy photons to pass through to the localized area on the patient. And surrounding the cathode and the anode system is the vacuum chamber. It ensures that the entire system remains unaffected by any external variables. Some of the diagnostic imaging that uses the X-ray tube include computed tomography, conventional X-ray, and mammography. Computed tomography, or CT, uses X-rays in order to produce cross-sectional images of a person's body. These images can be combined to create a three-dimensional image to use for diagnosing illnesses, masses, bleeds, etc. Using the photoelectric and Compton effect, the CT sends X-rays through the body and the scanner will generate an image based off of the distance the rays travel to reach tissues inside the body. As the X-rays are emitted in a continual rotation, the CT images produced are more detailed, and with the cross-sectional views, radiologists and physicians are able to better observe irregularities within the body compared to a regular X-ray. CT scanners consist of the X-ray tube, gantry, and a computer. The gantry is a circle portion of the CT machine, as you can see in the diagram. It is the structure that holds the X-ray tube in dark blue and the X-ray detector in orange, which are spun with a rotating scan frame. Connected to the X-ray tube is the collimator in light blue, where the X-ray emission is manipulated to change the range dependent on what the radiologist is looking for, as well as limiting the scatter radiation to improve the quality of the image. The filtration, also in light blue, is intended to remove the irregular wavelength rays to maintain the consistency in rays that are emitted while reducing the radiation exposure to the patient. In the gantry, there is a slip ring in the green. It maintains the electrical power in the scanner and allows it to spin continually to produce the CT images. There is also the generator in yellow. It plays a role of generating a high voltage source for the X-ray tube. Along with the generator, as heat can be acquired from operation of the CT, there is a cooling system to ensure the components of the machine are not damaged from the warmth. Lastly, there is the X-ray detector, where the X-rays are absorbed. Information regarding the distances rays travel to and from structures within the body will allow the CT machine to develop multiple cross-sectional images of the body. In conventional radiography and mammography, the X-ray detector or cassette is where the X-rays are absorbed in order for radiologists to produce an image. The cassette is made up of plastic transparent screen, which is coated with fluorescent particles. As the X-rays reach the screen, they cause a reaction with the fluorescent particles, and the particles will then emit light rays onto the film. An image is produced from this reaction, and it will be visible to the radiologist where the photons were most absorbed in the body, creating obvious shapes, along with varying shadows where the photons were less absorbed. On the back of the cassette, there is metal that is often sprayed with some sort of lead in order to absorb any additional radiation. In conventional radiography, the person is positioned between the X-ray tube and the cassette. When the X-ray is completed, the radiologist then takes the cassette and uploads it to a computer where viewable for physicians. A mammography is much like a conventional radiography, however, it is intended for diagnosing breast cancer. This machine uses the top plate in order to flatten the breast towards the bottom plate where the X-rays are absorbed. The mammography machine then downloads what is absorbed onto the cassette, and images are then viewable from a computer. Ultrasound uses sound waves in order to produce images of the inside of the body, and it is most often used for obstetric ultrasound, observing the development of babies while a woman is pregnant. An ultrasound unit consists of a computer, scanner, and probes. Ultrasound techs have a variety of ultrasound probes to use. Depending on what is being queried, the tech will choose the appropriate probe. The shape of the probes will determine the shape of the view. A round end probe will create a rounder cone-shaped view, whereas a flat end probe will create a square view. In image 1 on the screen, we see that the image is rounded. A probe with a rounded end would be used to produce this ultrasound image. The diagram of the probe on the left would create an ultrasound image as we see in image 2 because of the flat face on the probe. The probes use quartz crystals called piezoelectric crystals that vibrate and change shape as an electric current is applied to it. These vibrations create ultrasound waves that are sent into the body. As the ultrasound waves meet different tissues in the body, they send back signals to the probe. The greater the distance into the body that the wave travels, the weaker the reflecting wave signals will be. With this, the scanner develops images using frequency of the waves reflecting back, calculating the depth by using the time it took for the wave to return to the probe. Some internal properties do not reflect waves back, such as fluids, blood, amniotic fluid in the womb, and urine. These will appear as black on the image. In ultrasound, they use the Doppler effect in order to see the movement and direction of fluid within the body. The Doppler effect is how the observer will perceive sound differently depending on whether the source of the sound is moving towards or away from them. By this, the ultrasound machine is able to determine the direction of the movements by the frequency that is detected by the probe. The direction of the movements appear on the screen in different colors. This is often used when observing arteries. It is fascinating to think that more than 100 years ago, scientists were only playing with ideas in a lab and stumbled upon something so changing for the world. So many lives have been saved due to these discoveries, and it is amazing the fact that even today, so many changes continue to improve healthcare. especially how technology allows us to be able to complete procedures with greater success rates and recoveries than ever before. I found this topic so interesting, and this is only a skim off the top of the several other types of diagnostic imaging, with their backstories and how they have much improved today. Thank you for listening.